Hey, Cat 3 class, we're going to look at how do I come up with the change from rectangular coordinates to spherical coordinates if we are going to do a triple integral in spherical coordinates. So I wanted you to see where this comes from. It's very similar to when we did polar integrals and we had that extra r, or cylindrical coordinates and we had that extra r because of the polar change of x and y to r and theta. We had the extra r dr d theta, or r dr d theta dz if we were doing cylindrical. So here is rectangular coordinates, and notice again I've got for triple integrals I would have instead of a rectangle in the plane, I have a rectangular box in space, and now we are subdividing this region into smaller rectangular solids, and the dimensions of those rectangular solids are delta x, delta y, and delta z. And when we take the limit of these volumes, those delta x, delta y, delta z, sorry, the limit is these go to 0. Those delta x, delta y, delta z's become dx, dy, dz, the differentials. And I want you to see what happens when we look at differentials in spherical coordinates. Alright, so spherical coordinates, if you look really close here, we got obviously there's a sphere there with radius 3, and if you look inside of there, there is a dotted dash black line, and that is our value for rho initially. So I move this up and down, we see that dotted line, rho, grows as I slide that slider back and forth. So there's my value for rho, and then remember the first angle we talk about is phi, and that's coming off the z-axis towards the x-axis, and so that would be my angle for phi would be coming off of there this way. And then I have the next one is theta, which moves that point off of the x-axis into towards the y-axis, into quadrant 1 or octant 1 in this case, since we're in space. Okay, so there would be like a polar point. Now the idea here is with differentials, just like it was with these deltas, delta x, delta y, delta z means a change in. So with these with this picture down here, what we mean by a change in, let me pick a color right here. So let's say that I was at this point right here, and this was my initial point, and from being at that point to being at that point, a new point in this plane, or this space down here, I changed in the x direction by this much, so this is delta x. I changed in the y direction by this much, and I changed into the z direction by this much. And I could have multiple paths to get there, y first, then x, then z, z first, then x, then y, z first, then x. We have all these different paths to get there, but that's what we're implying by this change from one point to the next point. I'm changing by this amount in x, y, and z direction. So it's a change. And we can see that change with these differentials. They represent the change. And the idea is delta x, delta y, delta z are small changes. But we get these 3 dimensions of change. So let's look at it in spherical coordinates. What does change look like here? Well, let's start off with change in rho. So remember, this is rho. It's the length of this dotted line segment. If I add to that, what's going to happen is that's delta rho. That's an extra piece coming out of the rho that's already there. So there's my delta rho, if you will. So this is rho, what rho already was. This is delta rho. Okay, now the other 2 are angles. So if I have, again, phi is this angle off the z-axis, coming down towards this black line. a change in that would be coming off further. So if I start sliding this, you see we take rho and we extend it down further, and that's delta phi, that angle down there. So this angle, or you can think of it as this angle, this is the change in that angle. So we did go down this far to this line, and now we've added to that this delta phi. All right, and then finally the last one is delta theta, the change in the angle that sweeps us from the positive x-axis in the direction, if delta theta is positive, it swings us in the direction of the positive y-axis. And so let's start swinging that out, and we get this shape as I swing that around. All right, and then this is what a differential is going to look like. Okay, if we add more, so we're out on this radius, a radius of 3, and we extended that radius, that's delta rho. We rotated our angle down off of the z-axis by that amount that corresponds to that green. We'll just talk about what that is in just a second. And then we rotated further from the x-axis in the direction of the y-axis, and that's represented by this rotation right here. All right, so anyway, that's what a differential looks like. Now I'm going to take away the sphere. I'm going to take away these little guiding lines as well. These dashed lines that represent the angles and the changes in the angles. And so you're just left with the differential. So there's what a differential looks like. It's not quite, if you look at it from the side, you can see it's not quite rectangular. All right, you look at it from, well, let's look at it from above. It's not quite rectangular that in any direction because it's based on circular motion, rotation. So these are like little pieces of a circumference of a circle, what we call a chord. They're just tiny little pieces of a circumference of a circle. All the different values are, except for d rho. It is straight, but the rest are curved because they're based on circular motion. So if you recall arc length, how do we get arc length? Well, if we've got a radius of r and an angle theta in radians, then the arc length is simply just the angle in radian measure times the radius. That's the measure of that arc. So who here is measured with arc length, or pieces of a circumference? Well, everything in green and blue is measured in arc length, and the straight line is that delta rho, again from our picture right here. All right, so let's derive, what are these? Well, the easiest one again is delta rho. All right, now what we're going to do next, I want you to understand how I'm coming up with this. We're going to, even though this is not quite like a rectangular solid like this was, so where the volume of this little red rectangular solid was delta x, delta y, delta z. Once again, this is not quite rectangular because there's bends in these blue and green pieces. So it's not quite rectangular, but if we can zoom in on this, if I make these side lengths shrink, which remember that's what happens, we let delta x, delta y, delta z make their way to 0. We take a limit when we get a definite integral. The same thing is going to happen here. If I take a limit as these things shrink down to nothing, these differentials, these delta rho, delta phi, delta theta. If we shrink those down to nothing, the limit of this change, we do get something that resembles a rectangular solid. If we make these changes so small you won't be able to tell that these things are bending. It's the same thing as if I'm looking at a graph somewhere that obviously is bending, but if I keep zooming in and making the left to right change really small, eventually you zoom in on this thing that's obviously curved and it looks straight. And that's when we have really, really, really small numbers in there. Well, that's the same concept of what I'm trying to do here with this. If I zoom in small enough, if I make the deltas small enough, and these left to right changes are teeny tiny little fractions like they were here on this page, we get stuff that's virtually straight. And so we can then say that this is a box, and its volume is the red times the green times the blue. All right, and I'm going to use the bottom here instead of the top, just because it's easier. It's easier to work with. But if I take this green, and I made them a little bit different color. I don't know if you can notice that. I made them a little bit different color because I want to distinguish the bottom from the top. But I'm going to use this darker green, this darker blue, and the red as the length, width, height. All right. So what's the volume of a box? It's the volume of the area of the base times the height. So the length times the width times the height. And that gives us the volume of this thing. So we're going to do the same thing here. We're going to find, we know the red is delta rho. We're going to find the green length and then the blue length. Okay. Now let's go to the green. The green is, if we go back to our box, I'm going to make it a little bigger. The green is on an arc path, a circular path. So let's think about it. Where is it coming from? It comes from rotation. So from that down to that. Now again, let's think about the bottom end here. If I change that delta phi, that green thing gets bigger. Now we're using the bottom one, we're using this darker green. So this was right here, this was the original phi. Okay? And for that black, that's the original rho. That's not the rho plus the delta rho, that's just the original rho. So the original rho rotated by delta phi is that darker green on the bottom. So the original rho and then rho delta phi. Okay, when we're looking at the arc length of that green piece, dark green piece. So once again, this down here is where rho originally was before we added delta rho. So this is rho, that green was rho, and then the green was delta phi, or the angle was the change in phi. So we get, for this one, we get rho, and the angle is delta phi, and that's this side length. All right, so rho delta phi. All right, now finally the blue. So if we start here again, let's use this blue, the one that's closest to where we originally started. We originally started here, we rotated down, and we rotated right and extended. So if we're originally starting here, that's again with rho, and then this angle right here is theta in the XY plane. Let me go back to the picture. All right, so again, think about originally starting here, and we rotate at this point. Now here's the thing. What are we rotating when we go left to right? We're not, notice this right here is, this guy right here, this is rho. I'm not, like, this is not, this blue arc, if you look at it, what we're rotating around here, that's not rho that's being rotated around here, because again, it has to make a circle. And if you see when we did what we just did, this was rho that was rotating along that green path. That is rho that's being rotated there. That is the radius of that green piece that comes off of there. But here, the blue, that is not rho when we rotate this way. that's not coming off of this circle. So let me show you what it is. It's, if I turn on this so you can see the circle that we're on, that straight line there out to that is not, that would connect the center of this circle out to here. That's the radius. And that is not rho. This is rho. This is not rho. Alright, so what is this? What path are we on here? Well, think about this. If I extended a straight line out from the center of that circle out to where we're hitting that initial place, that angle right there, that is phi. That's the angle phi on both sides here, on the inner part and the outer part. It's still phi. And then this dashed line is rho. Where can I put that? Rho is that length right there. So this is phi, this is rho. Well, let's call this x. We don't know what this is. You know, some unknown value. But look, I've got a right triangle. This is where the right angle would be, since we're coming perpendicular out from the z-axis to hit there. And this is our angle phi. So this is opposite. X is on the opposite side. And then rho is the hypotenuse. So what angle involves x and p, or what trigonometric function of our angle involves x and p? It's the sine. The sine of phi is equal to x over rho, which is opposite over hypotenuse. So what is x equal to? X is equal to rho sine phi. And then we are rotating that distance around this amount, and once again that is theta that we're rotating by. So if I go from there to there, how much did I rotate? I rotated by theta, or delta theta. Delta theta. So this blue line segment is rho sine theta, and we're rotating by delta theta. So again, according to arc length, that's delta theta. This is rho sine theta. I'm sorry, I said that wrong. This is rho sine phi, and then this angle is delta theta. So this blue line segment is going to be delta theta, and then the r, the radius, is rho sine phi. So rho sine phi delta theta. And again, all these deltas are going from what they are to 0. So the volume of this little differential, this little volume differential, delta volume, if you will, is approximately equal to, and it will become this as we take a limit, delta rho delta phi, and rho sine phi delta theta. And if you look, we got a couple of rows in here that are on their own. They're not delta rows. So to clean this up, the way we write it is rho squared times the sine of phi times delta rho delta phi delta theta. And obviously you could do those in any order that you want to, but here's the key thing. When we take the limit as these little shapes make their way to 0, these deltas will become differentials, and we get the triple integrals over some space, and we're going to describe our integral with rho phi and theta. And our differential now is going to be rho squared sine phi, and then d rho d phi d theta. Alright, so there it is. There is triple integration in spherical coordinates. If we switch our integrand to spherical coordinates, rho phi thetas, then we have to make sure, just like we had to do with polar, we had to have that extra r. Well, now this is what we have to have in there. Alright, then we have to have this concept in there twice. And so it's the extra r, really 2 times. Rho is kind of like r, and then rho sine phi literally is r. It's rho sine phi is the idea of r and polar, and so we have a rho and then a rho sine phi. It's like rho times r is showing up when we switch to spherical coordinates.